In this video, we're going to discuss electric potential. Electric potential is the potential energy per unit charge. So we have to be very careful with wording because there is a difference between potential and potential energy. So it's very important when you're reading a problem to make sure that it does not say potential energy versus saying potential. So as I just said, potential, represented by capital V, is potential energy per unit charge. So it means it's going to have units or joules per coulomb, or what we're going to reduce into volts. So you're going to start to see this form between our theory here and what are going to be more practical applications of electronics in our next unit. Potential difference is going to be the change in potential energy per unit charge, or what we typically refer to in mechanics as work. So it's the work to move a charge, so an imaginary test charge in the electric field, from point A to point B. So you can imagine putting the voltage pros of a multimeter between 2 points. So you're measuring the voltage between 2 points. So if we want to calculate the potential at a given point due to a point charge, we need to use the potential energy equation. So I plugged in the potential energy equation specifically for a point charge, and then I divide by the test charge. So it's potential energy per unit charge. So you're going to have your Coulomb constant divided by the distance between the charge and your point of interest, so where you want to know the voltage at, and then the Q. So that Q is the one that is generating the electric field. And notice once again, there are no absolute value signs in this equation. So if I want to find the potential at a particular point due to a bunch of charges, then I would need to sum over all of those charges. So take the charge divided by the distance between the charge and the point of interest, sum all those together, and then multiply by the Coulomb constant. Alright, so what if we have something that isn't a point charge? What if we have some other distribution of charge? So we have this other form of the equation that allows us to calculate the potential difference. So we're going to take our electric field strength and dot it with dl, but we have to remember we're also integrating that electric field in terms of L. And so in order to use this equation, we first have to sub the electric field equation for the distribution of charge in the particular problem. And then we have to keep in mind dl is the straight line path between A and B, which means that depending upon which electric field equation we're using, that may actually be dr instead of dl. So something like if you have a linear charge or a line of charge and you want to find the potential difference between the surface of the charge and some radial distance away from the point of charge, you would have to replace the dl with dr, because that would be the radial distance away rather than some length away. So you have to make sure that this L matches up with the same variable in your electric field equation. And this equation is going to come very important in topic 24 as we begin to calculate capacitance, actually. This is going to how we determine how to calculate capacitance, believe it or not.